Dragonflies the size of hawks. Centipedes larger than humans. A strange menagerie of giant insects and amphibians reigned over the Earth 300 million years ago. Over time, these huge creatures shrunk in size or disappeared. The reasons for their progressive extinction remain controversial. $358 million years ago, the continents came together to form the supercontinent, Pangaea. This was the beginning of the Carboniferous period. Oxygen levels in the air were much higher back then, 35% compared to today's 21%. For the first time on Earth, giant trees stored carbon dioxide and released oxygen in abundance. Human beings would not have survived in this high oxygen atmosphere. But for some swamp dwellers, it was ideal. Like Arthropleura, measuring up to 10 feet. This long-lost cousin of the centipedes was a herbivore. Or Meganura. With a wingspan up to 25 inches, this member of the dragonfly family is the largest known flying insect ever discovered. A tireless predator. It had no airborne competitors at the time, since birds and flying reptiles didn't exist yet. The high oxygen levels in the atmosphere give the characteristic sepia color to the sky during the Carboniferous period. Oxygen also makes the air extremely flammable. Such a hostile world is hard for us to imagine. Lightning storms could set aflame the immense forests and their inhabitants. During this period, not a day went by without huge forest fires, and yet giant insects thrived. Later, when fires became less frequent, these astonishing creatures simply disappeared. Scientists are trying to determine what caused their extinction.
There are several possible culprits. In fact, it's a bit like an Agatha Christie novel, when there's not one, but several murderers. It's our job to take the clues we have and reconstruct the investigations in order to come up with the most likely scenario.
While we've known about giant insects since the 19th century, paleontologists did not understand why they had disappeared. For a long time, a change in the composition of the atmosphere was the only explanation. But at the beginning of the 21st century, the discovery of fantastic fossil insects and their predators opened up new possibilities.
While that's a wonderful hypothesis, and assuredly something was preying upon these giant insects, we don't have great evidence for it.
Around the world, American, European, and Chinese scientists confront the old theories using new fossil discoveries unearthed by groundbreaking technology to try and explain why these giants became extinct. The earliest giant insect fossils were found in the French region of Allier in 1880. Under the surface at this pond were the remains of animals that had died 350 million years ago during the Carboniferous period, Meganuras. Now extinct, these tireless predators are the largest flying insects that ever existed. This abandoned industrial site was an important coalfield in the 19th century, and as the coal was dug out, fossils were discovered close to the town of Commentry. The owner of the coal mine, Mr. Moni, gave his name to the specimen that is preserved at the Natural History Museum in Paris, Meganura moni. André Nel, a paleontologist whose speciality is early insects, watches over this valuable piece.
Miners would look for fossils to make a little extra money. And one day, when they were opening slabs, they came across this animal. Unfortunately, when they were digging it out, they hit it 4 times with a pick and we lost its head. They were the super predators of the time, predators of other insects that were also very big.
These large-sized fossils are quite exceptional. While thousands of insects were found on the site of Carboniferous, only 5 Meganuras were ever discovered.
Meganura, like all other insects, had 4 wings, 2 on each side attached to the thorax in the center. In front you had a head with big eyes because it was a predator, so its eyes, just like modern dragonflies, were used to see its environment in 360 degrees, so possibly even behind the animal.
To better understand how this extinct animal once lived, we must step back 300 million years in time. This is what the French region of Allier would have looked like then. A giant swamp scattered with cypresses. Humidity at nearly 100% made the atmosphere dense and allowed Meganura to easily carry its heavy exoskeleton into the air. It is part of a genus that is extinct today, but it looks much like modern dragonflies and is part of the same Odonatoptera superorder. With wings that functioned independently of each other, Meganura was agile in flight, but unlike its contemporary cousins, it couldn't fold its wings. Faced with this efficient airborne predator, vegetarian insects such as Paleodictyoptera had to keep themselves out of sight. By comparing its anatomy to modern dragonflies, we can guess at Meganura's main physical characteristics. 1, it could fly over 40 miles per hour. 2, it was a sight predator. Its head was independent from the rest of its exoskeleton, so it could keep it still while flying and focus on its prey. 3, it had a huge appetite. It could eat its own weight in food every 30 minutes. To catch all this food, Meganura had an array of attributes identified in fossils. But what might explain its giant size? Away from the public is the museum's library of species, where they keep the specimens that scientists study. Here we find Meganuras and their prey, both reaching impressive sizes.
So here you have an example of a Meganura, on which we see the base of its wings, the thorax, but what is most spectacular are the 4 legs equipped with strong spines that were used to stab prey. But the Meganura's prey were also large-sized insects, like the Paleodictyoptera. You just have 1 wing from here to here, so you can imagine the whole thing. These were Meganura's prey. They were big guys too. Big insects to escape big predators. So in this case, we have an arms race between predators and prey.
But this battle to be the biggest between Meganura and its prey seems to have had its limits. Otherwise, paleontologists would certainly have found even bigger and more terrifying flying insect fossils. Most of Meganura's day was spent looking for food, since its metabolism required a lot of energy. According to scientists, the huge size of insects during the Carboniferous period was possible because of the high levels of oxygen in the air. Insects don't have lungs, but instead use a unique system of tubes, trachea, and tracheoles to bring air directly to their organs, including their digestive system. The downside to this system is it lacks efficiency. Air travels through the tissues in the form of gas. The bigger an insect is, the more oxygen it needs.
It is very strange that these animals reach these sizes, because nowadays we do not have such big insects. And at the time of the dinosaurs, when we had large vertebrates, insects were much smaller. It turns out that in the Carboniferous period, for reasons linked to geochemistry, the oxygen rate in the atmosphere was higher than it is today, which encouraged the development of animals such as the large insects.
Meganuras could not survive in today's atmosphere because not enough oxygen would reach their organs, including their brains, and they would faint. Since the beginning of the 20th century, scientists have proposed a link between the size of insects and the concentration of oxygen. But it wasn't until 2007 that an experiment finally proved it. In the Chicago suburbs, the Argonne National Laboratory houses the United States' most powerful Synchrotron, a scanner that generates the brightest X-ray beams in the Northern Hemisphere. The distance around the particle accelerator is more than half a mile, so Jake Soka, the scientist in charge of the study, uses a trike to get around. Today, live insects are being put under the scanner.
We use the idea that you can take living insects and make inferences about insects that existed in the past. What we're trying to do in this study is to test an old hypothesis that the amount of oxygen in the atmosphere is what limits insect body size. So the idea with this hypothesis is that when you have more oxygen, your insects can get larger, and when you have less oxygen, insects will get smaller in response. But no one had really ever tested this hypothesis before. So we use synchrotron X-rays to look inside the animal to study the dimensions of their tracheal system.
This particle accelerator generates extremely intense and focused X-rays that pass through the insect's body.
Our purpose is to see the tracheal system in action, and some of the tracheal tubes are really small, and we want to see it in the living animal. So this is really the only technique where we can do all of those things.
For the first time, scientists are able to actually observe an insect breathing.
Would you turn the beam on?
Using this experiment, they discovered that crickets not only breathe passively, but also use their whole bodies to carry air to their organs.
And you can see that bubble in the gut moves forward to the head, then it moves backward. And every time it's doing that, it's synchronized with the compression of the tracheal system. The movements that you see here are not a passive effect. This is an active movement by the animal, and it's the ultimate cause of it are contraction of muscles.
Just as this cricket contracts its digestive system to send air to its organs, Meganura would have contracted its abdomen to absorb the thick Carboniferous air. The elastic exoskeleton would resume its shape once the muscles had completed their action. But beyond the discovery of this internal movement, what interests Jake Soka is the space occupied by the respiratory system within the insects' bodies. He has compared beetles of different sizes to study the link between their size and that of their respiratory system.
And what we found is that the tracheal tubes take up a larger fraction of the body as you go from smaller to large than you might expect. So what we think, based on the study, is that if you would make this even larger, so if we would scale this up farther and farther, eventually you reach a limit where you can't stuff more tracheal system inside the animal because you have to have other things like muscles and gut and nervous tissue, fat bodies, things like that, that are all important for the physiology of the animal. You can't just have one big tracheal system.
The higher oxygen concentration of the Carboniferous period meant that insects required fewer respiratory tubes and could therefore grow to a larger size. But with the modification of the atmosphere, the giant insects had to reduce their size over millions of years of evolution. And not all of them survived these changes. 290 million years ago, during the Permian period, oxygen levels decreased from 35% to 23%, close to today's level. Pangaea had already formed a supercontinent extending from one pole to the other. Surrounded by a single ocean, it was subject to extreme climatic conditions. The heart of the continent suffered drastic temperature changes, and deserts appeared. But at the equator, heavy rainfall allowed the great forests from the Carboniferous era to survive. During this